Welcome to EDU World Space.
Here we're going to be looking at the design of a solar sail. A solar sail is a concept of using starlight to propel a spacecraft, using a large area, usually reflector, and we'll see why a reflector is typically desired. But what you're using is radiation pressure from sunlight, and recall that pressure in general is a force per unit area. And it is, of course, using Newton's second law, the force that will propel the sail. So that force coming from the pressure is equal to the mass of the sail times its acceleration. How do we calculate the radiation pressure? What we need is the flux from the star, of course, in this case, the sun, driving the sail. The flux from the sun or the star, we will write as the average value of the pointing vector. And we need to divide by the speed of light. This is, after all, sunlight. And this is typically what you would use for a dark surface that absorbs the light. For a reflective surface, we would get twice the pressure because there's twice the momentum imparted to the object by a photon bouncing backwards compared to just stopping. The flux from the sun we can write down. I'll say a little bit about how you find this, but it is a well-known value known as the solar constant. It has a value of 1365 watts per meter squared. And this is the flux from the sun at the Earth. So we will assume that the sail unfurls at 1 astronomical unit from the sun. And a reminder of how you find that flux. You basically take the luminosity of the sun and you divide by 4 pi times the distance squared. And the luminosity basically comes from the Stefan-Boltzmann law, the area of the sun times the Stefan-Boltzmann constant times the temperature to the 4th power. And of course, the area of the sun is 4 pi times its radius squared. And that surface area through which all that energy radiates gets larger and larger as you get further away. And this is why you have an inverse square law. Okay, so yeah, that's all embedded in there, but we're just going to assume that this solar sail starts at 1 astronomical unit away. And we are trying to calculate the radius for a fairly strong acceleration of 9.8 meters per second squared. So putting this all together, what we have is force is mass times acceleration over the area of the sail, which we're assuming a circular sail, and normal incidence. That's another thing. normal incidence of light so that there is no cosine squared angular dependence. So this is force per unit area is equal to the Poynting vector over c. And we can cross multiply and take a square root. And use the numbers given. And check the units that it does come out to be in meters. It's not too hard to do, but we'll use all SI units. And we get, I will write this in terms of kilometers, I think makes a little bit more sense. 90.7 kilometers. And this is for the dark surface on the sail. For the reflective surface, what we see is that because the force per unit area, the pressure is twice as big, there will be a factor of 2 down with the S in the denominator. And so the B is going to be down by a factor of square root of 2. And it is still huge. Now, typically, you don't need a solar sail this large, although it would be helpful to have it. The idea is that there's kind of a critical acceleration that you need, which can be easily understood by considering the force of gravity from the sun and the force from the radiation pressure. The force of gravity is, of course, determined by gravity, but the critical acceleration is when F radiation pressure is approximately equal to, but a little bit larger than the force of gravity. And so we can think about the acceleration due to gravity of the sun as being kind of like a critical acceleration that you need to achieve. And that is equal to, we'll divide out the mass of the spacecraft. So we get gm of the sun over the distance squared, which we have already said is 1 astronomical unit. So we put in our numbers, including the mass of the sun. And 1 astronomical unit in terms of meters. And we get a very small acceleration. Which is close to 1,000 times smaller than the acceleration that we're looking at. So we can imagine that the acceleration we need is maybe 10 times this, or 100 times smaller than what we are expecting with a 9.8 meters per second squared And this would get the size of the solar sail down by a factor of 10. More reasonable, but still city-sized type of object.